All right, hello. I'm Jesse Wilson, and I'm here to talk to you about mobile and memory. But first, let's make some breakfast. I got my kitchen, I got my recipe book, I got my pancake ingredients, I got my berries that I'm chopping up, I got my smoothie ingredients, and I'm ready to put the pancakes on the table. And this type of process happens to me every Saturday, where I use every single square foot of my kitchen counter to prepare breakfast. And I feel like the kitchen countertop is this like contentious, important space in my life where I want to have enough counter space so that I can actually, make the pancakes right. And the way you make breakfast, the way you make dinner, or the way you use your kitchen, you got to allocate space on the counters, do the stuff in that space, and clean it up again. And the space in your kitchen counter is precious. The more counter space you have, it lets you do more things. If you have like a New York apartment, you just don't have that much counter space, and it means you just can't make the pancakes and the berries and the smoothies all simultaneously, and it's really difficult if you want to make yourself a Thanksgiving dinner. So when this counter space is tight, you thrash. One more thing about counter space I want to call out is that there's like a locality concept to it. So if you even have a ton of counter space in your kitchen, if you've got like the half of the ingredients over here and half the ingredients over there, it's difficult work to build that breakfast or to build that meal. And you're just constantly just going back and forth across the kitchen. And I'm talking about counter space because the counter space is sort of like the working space of breakfast, and the memory is the working space of our applications. And I feel like there's like a really close metaphor here. I talk about locality as like a real concept that we experience in the real world. Well, in your phone CPU, there's like a 64-byte cache line. And when you say like, read me this value from memory, you're actually going to be reading a bunch of adjacent bytes for that data. And if you access that adjacent data, it's free. You've already walked over to that part of the counter. And so I want to talk about memory, but I'm going to keep coming back to this kind of metaphor. But enough about breakfast. Let's make an app. This is an alligator themed droidcon talk. And so we're going to do an alligator themed app. I bake some pies. My plan is to bake a pie for every alligator in the world, and we're going to put a little Bluetooth receiver in it. We'll buy a bunch of air tags, and then we're going to go out and we're going to pay some interns to feed pies to alligators. This is a tech startup. We're going to put pies in alligators. That's going to be our way of installing Bluetooth receivers in alligators. And then finally, we can sell our app in the App Store so that when your app detects the alligator, it can alert you, all right? And so I've gone out. I haven't actually installed the pies in the alligators yet, but I wrote a Compose UI, Android app, and a Swift UI iOS app, doing all the cool Kotlin multi-platform stuff. And right now, there's this one button in the app that says Show Nearby Gators. And for my talk to work, you have to pretend that we're going to come back to the screen, press Show Nearby Gators, see them, leave, come back again, show Nearby Gators. Maybe we're going to have buttons to say, show gators near me, show gators near my children, show gators near my parents that are, I want to make sure that if anybody I know is getting eaten by gators, I'm finding out about it quick. So you click the button, and then suddenly Allie, the alligator, tells you how far Allie is, and you're like, well, it's time to get out of here. Or maybe you're walking around and there's just like a swarm of alligators coming. So it's a really highly important application to save lives. And so here we are at DroidCon to talk about this application and just how it is going to interact with our program's memory. The dump of this code, I've got a couple of shared classes, a nearby gator and a gator service, and then UI for both platforms. And I'm just going to go through all the code, and then I'm going to take that code and I'm going to put it in memory and just show you exactly what's actually happening inside your phone. So we got the nearby gator class. We got the gator service that runs on Bluetooth, the electromagnetic radio signals of Bluetooth. And the way that this service works is not how our modern stateful classes work in Compose. You can't just like add a listener, remove listener. There's like state classes. But the way that the hardware works is like you say, add a listener, that like boots up some radio mode, and now it's like actively listening for alligator attacks. And then when you're done, you remove the listener, and that turns down the radio and saves your phone's battery. And then if we want to actually take that thing and use it in Compose, you need kind of like a glue class like this. My glue class is called nearby gators content. And so I have a state variable, the list of gators near me. And when you create this thing, it's subscribing to gator events and updating that list that's on the screen. As we get this thing more powerful, maybe we're going to have ways to add listeners for different locations, different sizes of gators. Maybe we'll sell a tiger add-on for a monthly subscription or something. And then because this is 2024 and this is droidcon, I'm going to just punch a bunch of Swift code into your eyeballs. This is the nearby gators content. This is called combine. I think combine is like the coroutine statey thing in Swift. And so we have exactly the same code, but written in Swift. If I hadn't changed the syntax highlighting and added the little Swift bird, I might have tricked you into thinking that this was just the same Kotlin code. Finally, some Compose UI. Every time you push that button, I'm going to create that content thing. And then when you dismiss it, it's going to go away. And the Swift one is exactly the same. If you get anything away from this talk, it's that you should just put Swift UI on your resume, and you can start getting those big paying Swift UI jobs because it's the same. Finally, 22 slides in, I'm going to start talking about memory. So throughout the way that I'm writing code, I'm not thinking about memory sort of as it's physically structured. I'm just thinking about how it works as I interact with it. And I interact with it kind of like my mental model is, I write these lines of code to create Chompy, and in memory somewhere, there's a little object that has those fields and the type. But the memory is actually a little bit more complicated than this. That name field isn't actually inline. There's a reference to a string. And so in theory, if you got two strings, both chompy, you don't need two copies of that string in memory. They just point to the same location. And it gets more complicated. That string isn't just 6 characters in memory there. It's actually a different reference to a character array that knows its length and the individual characters. And so everywhere in memory, the thing that you're sort of logically interacting with is the maximally simplified form. So we got not actually a string, it's a character array. The class type isn't actually, a header on the object in the node. It's actually another field. The dot class in Java or the : class in Kotlin just looks up that extra member. And then that class points to a class symbol in memory. And we can just do this all day. The class symbol of any points at that thing. There's an any class in memory, and I'm kind of tricking here. It's actually the object class. But then the class is a class yo dog, and we can just go around and around in circles. And the whole program is just this big web of objects. And object is how we conceptualize our programs. It's I got nearby gator chompy, and we can just follow this all the way through. And even I got class is class refers to itself, of course. And there's a whole bunch of things I didn't even put in this diagram, so I have to just point them to arrows in the appendix. All right. So that's our logical memory. I want to go from this model to the closer to what's actually happening inside my phone. And so the first thing is that I've got 5.5 and letter C, but that's not actually how memory works. It doesn't have types. It just has ones and zeros, So we'll replace those things with the corresponding hex codes, and that is where I will stop going deeper in the how memory works. But the key thing I want to talk about is that logical memory is a graph. When we're working in our programs, we've got this graph of objects. We've got Chompy, we got the string Chompy, we got our Gator service, and every object is just literal values like chars or references to other things. And the way our programs work is just manipulating this graph, creating new nodes in the graph, changing the existing nodes, and even like when you interact with the screen, it's just like sending different objects or different bitmap literals to the screen. And now the big contrast, physical memory, not a graph. Take your phone. I got this awesome phone from a few years ago. I'm going to open it up. There's actual memory in there, all those chips. There's a thing called RAM, and that thing is just a physical implementation of a byte array, right? That is a 4 gigabyte byte array sitting in your phone, and there's not much more to it. There's no graph processor that's storing the logical memory. It's just this physical thing. And so we need a mechanism to bridge these two worlds, the programs that we write and the hardware that we have. And I'm gonna say that bridge is the allocator. It's the thing that goes between the big graph and the big byte array. And we'll go right in and find the simplest allocator I could find in our lives. If you write a bunch of weird Gradle code, including -xgc equals no-op, you will get the no-op garbage collector. And the way it works is every time you ask for a memory address, it just gives you the next one in a sequence. If you hand out 10 bytes, it bumps a pointer, and then the next 10 bytes, and eventually this program will crash because you will eventually exhaust memory. But if you write fast enough, short enough programs, this is a really, really fast garbage collector because there's no garbage collector. And so let's take our little graph. I'm going to build the no-op garbage collector and bridge our logical model to the physical one. So I'm going to say we're starting at 160,000 is the next offset, and our reference size is 4. This is like how many bytes does it actually take to reference one object to another. All those lines, there's no lines. It's all just addresses. So we're going to first assign an address to every single node in our graph. Right, so we put these little numbers on here. And why are the numbers going up by random numbers? It's because I counted how many bytes every object requires. So the first object is 10 bytes long, and so it increments by 10. There's a few things that I'm hand waving over here, like the objects have to, I think they have to be like byte aligned to 4 bytes or 6 or 8 bytes or something, but this is close. And now that we've got addresses for everything, we can replace the edges in my graph with memory. I'm going to replace all those decimal numbers with hex, and then I'm going to replace the edges with those memory addresses. And so now we've taken the graph abstraction, turned it into just pure data. And then I'm going to take that and that's Chompy, right? That's like that graph. That's what he looks like in memory. The real allocators, they don't keep everything they don't keep every single object that you ever allocated for all time. They have to cheat. They have to say, that string that is no longer used anymore, we're going to take that memory and we're going to give it back so that we can hand out that address again. Address 160,000, it was used for this thing at the beginning of the program, but that memory is no longer needed. We're going to garbage collect it, which means just reclaim that memory so it can be given to somebody else. It's much more like recycling. And so objects have no incoming references. The memory can be reclaimed, and we can write programs that create tons and tons and tons of temporary objects. You can create, a terabyte of temporary objects without running out of memory. I got 2 different techniques that programs will use to make this magic trick happen. The first one is the one we use in Android land, and mostly Kotlin land, is garbage collection. And so every once in a while, the garbage collector wakes up and finds all the dishes on the kitchen counter and finds all the unused objects in memory and frees everything. And this process is a batch process, and we have to walk through everything to say, you're using this, you're using this, you're using this, is this string chompy still useful? And so in this example, I'm going to make one slight mutation in my graph, and then I'm going to garbage collect it. So I got my nearby gators content thing, and I've got a list of gators. I'm going to pass in a brand new list. I'm going to call that onGators function. So if my original memory looks like this, I've got an activity, that nearby gators content that I'm going to call a function on. It points to a list, and that list points to a nearby gator. I'm going to pass in a new list with two different gators, and I'm just going to see like what happens to this in memory. So very first thing we do, we just take that list pointer and we make that change. That's like the code that you write, right? List dot something equals this other list. And then we invoke the garbage collector, and it says everything that has an incoming edge. I'm going to get rid of that because we're done that function call. Everything that has an incoming edge, we're going to just tick it off and say, this is still valid. So we tick all those things, and you'll notice that original list in Lyle, dead to us. We don't care anymore. That memory can be reclaimed. And so as soon as everything has been ticked, the garbage collector sweeps up everything unreachable. That stuff's gone. This is how memory works in Android, and it is wonderful. You are not appreciating how excellent this is. You got to appreciate it. Let's go look at those. Let's go look at what our friends are doing with their iPhones. So reference counting is a completely different paradigm that accomplishes the same effect, but wildly differently in practice. So rather than having a batch process, with reference counting, we track every object is responsible for self-destructing when it's no longer needed. And so in reference counting, we're going to again take this Swift code, we're going to call onGators again, and we're going to see exactly what this one looks like to contrast. Again, same stuff coming in. I pass in a new array and say, okay, I'm going to move this assignment from my old array to my new array. And so the very first thing I'm going to do is actually not just immediately change the reference. The first thing I have to do is I have to remove the old reference and decrement the ref count of that array from 1 to 0. And when a reference count reaches 0, it self-destructs. Boom, that thing's gone. And then it cascades. All the arrows leaving that object, now everything that they were talking to, they can self-destruct too. So that thing, gone, right? And then finally, this new arrow comes in and our array comes into focus. And so this is like a very different thing, both in terms of like when objects go away, but also in terms of like what things you can express. If you are writing Swift code, there's a function called dinit that is invoked when your object is going out of memory, because it knows precisely this thing is going away right now. And so you can do really, really powerful things like say, close files on the file system or release SQL cursors when something goes out of scope, rather than having to hound your programmers to call the close function. All right, so let's get to real business. Let's leak some memory. I got PY's permission to give this part of the talk today. PY is the author of a library called Allocator, which I will talk about a lot today. I'm going to go back to my kitchen, and right before I prepare breakfast, I'm going to invite the rest of my family into my kitchen, and just like all of their crap is just going to show up on all the counters, right? There's like, whose backpack is this? And it's preventing me from making you breakfast, you annoying children. So like this is what a memory leak feels like. It's like all of your workspace is just being taken away from you, and it's constraining. On the counter, wasted counter space wrecks your cooking performance. In your software, wasted memory wrecks your application's performance. And you can even do things like wreck the application performance for the rest of the phone because you're using more memory. You start leaking memory, and then suddenly a bunch of applications that are backgrounded get evicted from memory. So like next time you go to the browser, it has to do a whole loading phase because those tabs are gone. The impact of memory leaks is most severe for long-running processes, like you're writing web servers or web services. Eventually they crash if they just keep leaking memory. You're running like all-day applications like the driver app for Uber or the Square point of sale app. We're really serious about leaking memory because we want to make sure our application, you start it on Monday and it runs all week, right? So back to Gators. And while everybody was looking, I inserted a leak in this code. I added a listener to my nearby Gators, but I didn't remove it. And so I'm going to go to my app, and I don't have a slide for this, but I'm just going to go in and I'm going to open that dialog 6 times in a row. And open it, close it, open it, close it, open it, close it. And my hope is I just leak a bunch of stuff. And then now that I've leaked it, I'm going to show you all how we find that leak. So here we are in Android Studio, and you double tap Shift to open this guy, and you could type profiler. There's probably a better way to find stuff, but that's the way I do it. It opens up this excellent new task focus thingy, and there's a button called Analyze Memory Usage. It's so easy. You push that thing, and then you search for your nearby Gators content, and you can see I got 6 of them. So every single time I call that thing, it creates it, and nobody's cleaning it up because I forgot to remove listener. So we got 6 of those in there. One other thing that I want to call out, you see these random numbers at the bottom? I got like nearby Gators content at 315 something, something, something. That's the memory address. Like in that earlier slide where I put memory addresses on stuff, that's the memory address. And just to make it extra confusing, there's 2 numbers there. I opened them up in my calculator, and the first number is just the decimal version of the second number. So those 2 numbers, it's a little bit redundant, but okay, let's go do that in Swift. Same thing, same leak, open, close, open, close, open, close. And now we're gonna go into Xcode. Boo! We're gonna go into Xcode, and we're gonna find that leak in Xcode. Click on that thing. That is the share button backwards. And then you're going to get this guy, which has got, I think it's pyramids and hypercubes or something, Rubik's Cubes. And if you open this guy on the left-hand sidebar, you can see I pushed open close 6 times, and I got 6 nearby Gators content here. And now a brief diversion while I tell you how to tame Xcode. I got 5 Xcode tips. And these are like, there's like, boring things if you talk to iOS developers, but mind-blowing for me once I figured out how to do these things in Xcode. You're all Android developers, so this is like, you're like, nah, never gonna need it. Welcome to the world of multi-platform. You are gonna have to have Xcode on your computer. Maybe not tomorrow, but next year. Welcome, it's a horrible tool. All right, sorry. First thing you got to do is you got to flatten your Kotlin native allocations. So Kotlin native, when you say like, new nearby Gator, it doesn't give you a new node in the Xcode memory graph every single time you create a thing. It just shoves them all into one big composite object, which is great for performance. It doesn't need to tell Xcode every single time it's allocating a thing. But it means that this graph is useless because there's like 400 Kotlin objects in there, and I can't trace through and see like which thing of my Kotlin objects is leaking. So you like go into, again, more Gradle code, and you just paste this from my project example. The allocator is called STD, and STD will cause that graph to have lots of nodes. If you do this today, and you do a build, it will fail because you're not supposed to change the allocator without a clean build. And there's some bugs, and so you just like delete a random directory in your .conend file. And this was really painful for me to find out, but you do that, and then suddenly you go from like that one object to like a whole bunch of them. That is excellent. Xcode is hostile to you, and it will show you this diagram with a bunch of unlabeled pyramids and stuff. If you zoom in just a little bit, you see the nodes have labels. I was like, wow, like that is making my life so much better. But guess what? If you zoom in even more, the edges have labels, right? Like Like this was like the best day of my life when I found this. All right, if you right-click on an object and you say print description, it will run the object's toString function. This is incredible because it's not a static heap dump. This isn't like taking your heap dump of a dead program and analyzing what it left behind. This is the live program, and so you can actually run code. The print description will actually run, and I can see, you know, my nearby gator. That one was Allie. Allie the gator leaked. All right. Okay, this one's really hard to find, but just a gem. You go to your program, you go to Edit Scheme, you go to this thing, on that Diagnostics tab, you go over here, you find malloc stack logging, love Xcode, it just works, and then you do this, and finally, when you click on your object, you can open that thing, and then the reverse share button again, and you get a stack trace from when the object was allocated. This is so cool because now when you have this heap of just tons and tons of things, you know, you've got like nearby gators and alligators and probably like a lot of like composed stuff or buttons, you're like, where is the one I care about? You can actually see this was allocated by nearby gators content, and that's just like really, really helpful. I wish that the Android tools actually had this ability. Last one. So I'm like creating all these fake leaks and trying to find out, you know, what does my Xcode graph look like? One problem with this, though, is that my objects, some of them are legitimately leaked, but some of them, they just haven't been garbage collected yet. And even though I'm talking about how like Swift has reference counting, the garbage collector needs to run for all your Kotlin stuff. And so, you know, initially I run this, I got 132 instances of shared gator, and then I call this Kotlin function gc.collect, which is a Kotlin native function. And boom, most of those gators are gone. And so a really useful thing when you're using the Xcode memory debugger is force a Kotlin garbage collection somehow, maybe put it in your applications debug drawer or something, but force that GC, and then the graph, all the dead stuff goes away, and you can actually see what's actually still around. One other thing, this is all like the Xcode GUI, and I'm going to just shit on it the whole talk because it's fun. But there's actually some pretty cool, sophisticated stuff in the Xcode tool chain. In particular, there's a bunch of command line tools. So that heap that we produce, there's like a bunch of stuff for analyzing it. And you don't strictly need to use the Xcode GUI. All that data is available in like more civilized ways. So let's go leak some memory on Android. The answer is just use Leak Canary. Everybody uses Leak Canary? Critical thing of Leak Canary is that it already knows your Android objects' life cycles. It knows that like this fragment is dead and it should be garbage collected soon. If an object is still reachable in the big graph after its life cycle is done, it probably leaked. And this is just completely excellent. The other tool I want to highly endorse trying is called YourKit. You can export an hprof, a heap profile file from Android Studio, open that in YourKit, and you'll see that it's just much more capable than the little toy heap viewer in Android Studio. So here we're going to do that. We're going to take our leak, and we're actually going to fix the bug. We're going to remove the listener when it's all done. And now I'm going to just confirm that I fixed the leak. Loading Android Studio, push this past recordings button, even though it's like kind of like my current recording, you push that button, find the current recording, push this export button, and then you can open it up in YourKit, and I could see I got those 6 nearby gators contents. There's a word there, it says unreachable. So even though those things are still in my heap, that nothing is pointing to it, and it will disappear at the next garbage collection. So that's as good as dead. I'll call that a victory. All right, now let's do memory leaks on iOS using Kotlin native. So just use LeakSwift, it's really good. Nope, there's no person like PY in the iOS community. They don't have an awesome open source community. We do. We should flex that. There's like a couple of libraries, but each of them is like created, has like 3 months of commits, and then it was abandoned 5 years ago. So we're going to write that exact same Swift code. We're going to add our dinit function, not close. Dinit, how cool is that? You don't even have to remember to call it. And then we open this up in our boy Xcode, and we look and we see, oh crap, we still have 6 nearby gators contents. That makes crying with sunglasses emoji appear. So we didn't fix our memory leak in Swift, even though we fixed it in Android, and I wrote the exact same code. This is very, very painful, and this is basically how I've spent the last 4 months of my life, realizing that I can't take code I've written in Android, transliterate it into Swift, and have things work in a reasonable way. So I'm going to talk through what I wanted to have happen and what actually happened here. I got, again, my array of my nearby gators content, and in this case, I'm adding a listener, and then I want to remove the listener and make sure it goes away. So when I call the add listener function, and one other thing I should call about this diagram, the objects with blue labels are implemented in Swift. The objects with purple labels are implemented in Kotlin. This is the Kotlin multi-platform mind-blowing memory layouts, and you'll also see that the Swift ones have reference counts and the Kotlin ones don't. This is my world now. I'll have to reconcile that. So I call add listener, and that expands the listeners list, and then points a reference back to my nearby gators content. And so that increments its reference count. And now we have the biggest villain of this talk, the retain cycle. All right, so those two things are reachable because there's the inbound content. The reference count is 1. It never gets garbage collected. It never gets reference counted to 0. It's leaked forever. All right, so here's the solution. It's really straightforward. We take our nearby gators content, which has a gator service listener, and we extract the listener into its own nested class. And now the listener is its own responsibility, independent of the content thing. And then we make the reference back to the content. We use the listener, and then we have to do some wiring for the listener. Yes, this is a lot of extra code. But then we can make the wiring back to the listener, this thing, we can make it weak. And this weak word is, you got to use it everywhere in Swift. It's just a thing. So now I got that, and now this is how this works. So now I create this stuff. I call add listener. I create my little listener deal. But instead of having a regular arrow from the nearby gators content, from the listener back to the content, I got this dashed arrow. And what it does is it doesn't increment the ref count. So I have 1 strong reference and 1 weak reference. Now when I add a listener here, that thing goes to 2. I'm happy. And now when I remove my listener, I can clear that thing, because that is no longer reachable. It's only reachable by a weak reference. That can now go away, and then that can go away. And so the weak reference is the magic tool to break your memory leaks when you're working in Swift. Here's again a diagram just to prove I actually got it. I got 1 listener there. Hooray. All right. So working in memory in Kotlin multi-platform, when you're using Swift and Kotlin native, is just super difficult. It's like one of the hardest, most difficult programming things I've ever done. And it's because we've got these 2 different sets of rules, but we've got 1 graph that's playing by 2 different rules. You can even create retain cycles without writing any Swift at all. So in this case, I've got a holder object that I'm creating. I've got a 4-line Kotlin function, creates a holder, references the holder to an array and the array back to the holder. And that object, you call that function, and those things will be leaked forever. Even if you aren't writing any Swift code, if you're using Swift APIs, you're in trouble. So let's get really precise about these kinds of memory leaks, these Kotlin native Swift memory leaks. I'm going to say that these kinds of leaks, it's going to be a cycle in the big graph where at least one of the objects in the cycle is a NS object, which is kind of like the root object of reference counting. It's not really a problem if these objects are still in use. It's not, as long as I'm using the object, it's by definition not leaked. And the Kotlin native garbage collector will garbage collect everything as long as all the properties are Kotlin. So you can have cycles throughout all your Kotlin code. If you stay in Kotlin land, you're like still good. But as soon as you start involving APIs that come from the iOS Foundation libraries or iOS platform libraries, you're starting to make it possible to create leaks. And one thing that's like really critical here is that if you define an interface in Kotlin and you implement that interface in Swift, that object is poisonous. That object is reference counted. And so you're in trouble as soon as you like expose interfaces and implement them in Swift. You have to be really worried, like that's going to bite you. So now that I've introduced the boogeyman, let me tell you about a couple of strategies to fix them. So the way Swift programmers avoid creating retain cycles, this is all they know, is they just always worry about it. It's just like, when you were writing Java 5 to 10 years ago and you were like always worrying about null? You'd wake up in the middle of the night, cold sweats, null is gonna bite my feet. Well, that's how Swift developers are working today, and it's probably how they'll be working 10 years from now. It's just like weak references are a thing. And so if you ever read any Swift code, you will see like weak self everywhere. And that's just like, that's the thing. I drew this diagram of a memory leak. All right, so to avoid leaks in Kotlin native when working with Swift, here's how I do it. First thing is I never reference a Swift object from a Kotlin object. That's just like, that's easy, just never do it. And then you realize you have to do it. So rule 2 is when you break rule 1, first, give the Kotlin object a close function. It has to have a life cycle. If you're referencing Swift objects, everything that could reference a Swift object has a close function. That function sets all the Swift possibly properties to null, which is basically all the interfaces that could be implemented in Swift to null, or Swift types, and then make sure that gets called. So here's a class from a library I'm working on called Redwood. And we have this iOS API called CA display link, and it's a NS object. And so it has the display link knows about the target, and so now when I call close, I invalidate that thing, which is like its version of close function, and then I have to explicitly set it to null. You'll also notice that my display link class, as far as I'm concerned, it's not in its heart nullable. It doesn't want to be nullable. It doesn't like that question mark at the end of its name. But because I have to set it to null in my close function, I have to put garbage question marks all throughout my code so I can clear it to null. This process feels bad. All right, so why would I break it from Kotlin? I can use the weak keyword in my Swift. Like if I've got a reference that's like Swift object, Kotlin object, Swift object, there's lots of different places to break the cycle. As long as you break any one of the cycles, everything gets collected. And I've chosen in my programs to break them from Kotlin. And so I've got this fictional conversation between two mobile developers. This one says, "Did you get the latest Kotlin Allogators library?" And then our iOS developer says, "Yep, but Xcode is mad because it's leaking memory." And then the Kotlin developer says, "Oh shit." And the iOS developer says, "Oh shit." And that's the conversation. So it's equally valid to break cycles from either programming language. And Kotlin that doesn't leak helps to earn iOS engineers' trust. So if you're like, "Hey, iOS team, Kotlin's awesome," they're like, "No." And you're like, "It's really awesome," because they're just going to be skeptical. There's natural skepticism. There's a talk going on right now from Kevin talking about iOS skepticism of Kotlin native. A small way to earn their trust is to write libraries that don't leak, even if they use those libraries carelessly, even if they don't use weak everywhere that they should. You can detect leaks in tests. In Redwood, we created a leak watcher class. It uses a phantom reference, and so we create that, point a reference at it, and then when after we close the thing, we can assert that it's not leaked. This isn't a standalone library yet, but maybe someday. And then in production, we do the same strategy as Leak Canary. We have a leak detector API, and so it uses weak references behind the scenes in Kotlin native to see if an object is still referenced after it's gone out of scope. So, takeaways. What are we here for? Life comes at you swiftly. Garbage collection, awesome. Leak canary, excellent. iOS is neither. Every Swift object is a resource that you might need to release, just in the same way that you have to remember to close your files and your database handles and your network connections and stuff. And Xcode, it can be coerced into helping you. That's as strong as I can say. I've got one bonus topic. I'm just at time now, but I'm going to just go into one bonus topic because it's a memory topic and it's fun. There's this cool thing in JVM, not Android, not mobile at all, called Valhalla, and it's Java's epic refactor. And the JVM team's idea was, if we look at these graphs of objects in memory, it's all just references everywhere. It's all just arrows and memory addresses, but like the actual amount of real data is low, and that decreases the program's performance, and because like it's always just chasing pointers everywhere. So the idea of this Valhalla project is to unify primitives and references and get better null handling. So if you see JVM inline, it's like a spiritual endorsement of Valhalla as an idea. And so in Java source code, you'd take a class like nearby Gator. This is Java source code, not Kotlin. And then you would say value record. And that is a cool new thing that's going to make it possible to massively reduce the amount of references on the heap. And so in my little diagram here, I've got 3 gators that are threatening to bite my legs off. And so with Valhalla, the memory layout goes from this to this. And it's just great. It's just like everywhere that we have lots of different references, we can reduce them. And it'll make the Java programs even faster. For you, that probably means like faster Gradle builds, faster Kotlin compiles, faster IntelliJ, faster Android Studio. This project was started at the same time as droidcon. And but it's like, despite the fact that it's a very long project, it's not a project that's stalled. They've made really great progress, especially lately. And you can build you can get a build of JDK 23 that has it. So thank you for learning about memory on Kotlin and iOS with me.